It's really weird to hear my voice coming from a different place in the room. Hey, look, we're live. Question mark. Can you see anything? Sweet. On the subject of being good, how did the homework go last week? I'm assuming that you all did it last week, of course, because it was due at 3 p.m. today. Surely none of you were finishing up this morning, right? Ah, well, as long as it wasn't this morning, that's all I really care about. Did you have any discussion you'd like to have on it before we move on? Did it go swimmingly?
What's the easy way to get the equation from the graph to the, like to actually using it, just plugging it in?
The easiest way to do that is to avoid the graph altogether and to use the Linus. Yes.
I remember in seconds, I think you asked for time.
Yes.
Time, and like as far as Merkle result asks the time is Excel is different. It's like 400,000 something.
Yes, it is the number of days that have passed since January 1st, 1970. Yeah. That is a very common way of keeping track of time. Are you not familiar with that?
So isn't the key? It's like if, for example, I avoided time, like
if you. I mean, I would have preferred that you change the formatting to be a more conventional date and time, but technically that's fine.
Okay.
Any other questions or discussions you'd like to have? Did you guys all figure out the Linus function in regard to the polynomial or the exponential? Did you have any questions you'd like to ask on that process? Just talk about it once in case hypothetically anyone didn't figure it out and doesn't want to talk about it. Okay, so in the interest of hypotheticals here, what you were supposed to have done was to take the table in that homework assignments, Excel day 3. So you had a table that had a bunch of arbitrary years and population information. So I'm going to take that and put it into a new table manually like this. So 1750, 1800, 1850, 1900, 1950, 1990, 2000, and 2009. You, Mr. Gentleman with the hat and the green sweatshirt in the corner, is the live stream still going? Sweet. You're now going to be the official position responsible for informing me. Congratulations. It is an honor that I do not give out lightly. I feel a little bit like Dr. Keem now, just appointing positions in the class. Taylor, you can be class leader and or reader. Okay, population data. We had 791, 980, 1260, 1650, 2520, 5270, 6060, 6800. Okay, now if you wanted to predict the 1990 population, we could take that out here, use that as the argument for my Linus function. If I use the Linus function to output the first degree polynomial, I would say Linus, known y's, population data, known x's, year, constants.
1850.
Ah, yes, in the year 150. For some reason, the population was much higher than it was approximately 1,600 years later. I will go back and fix that. Thank you for bringing that to my attention. True and false for no particular reason. And then I will change this to 1850, much more better. Bring that back over here. Array function. We have 2251. I could type that in manually, or I could say 22.51, etc., times my 1990 value plus this constant equals 5,054. And then when I asked you for the error in each of them, what I wanted you to do was figure out the percent error, like you surely have done in a chemistry or physics lab report. And as a result of having a slight difference here, we can subtract them, divide that. If I wanted to be real fancy, I could use an absolute value. And apparently we have 4% error, which I could do by changing this into a percentage. Yes, do you have a question? Yes.
Not have used the line space function.
Okay.
Hypothetically, just copied and pasted the equations that appeared on the graph in the bar, and hypothetically changed
Yes?
and ended up getting the same answer, what retribution comes?
Hypothetically, if a student were to do that perfectly, by which you would have had to, I mean, hypothetically, a student would have had to have added a whole bunch of decimal places onto their equations, especially when we get into the third order polynomial and exponential function. That's technically still valid. It is inefficient, but it's valid, so you wouldn't lose any points for that. I mean, hypothetically, a student wouldn't lose any points for that. That is, again, assuming that it went perfectly.
It did not. Hypothetically, I ended up with like a 1,700% error for the three-order polynomial.
As a fun fact, that was why I included the third order polynomial, was because it really emphasized the incorrect methods of a student's efforts to solve the problem. You will get a non-zero number of points. Enjoy them. Other questions? Okay, so if we want to change this from a first order polynomial to a third order, what we have to do is add in a caret here in a curly bracket with 1, 2, 3, close curly bracket. I use Control-Shift-Enter, which is, of course, the shortcut that you've all programmed into your brain by now. And then I change this to a third order polynomial function, so it'd be e2 times d6 to the third power plus f2 times d6 squared plus g2 times d6 plus h2. Of course, we could name all these cells so we didn't have to keep track of random arbitrary letters and numbers, but keeping track of arbitrary things is really the nature of homework assignments within the mechanical engineering department, so it's something you should probably get used to. 2% error in the case of the third order polynomial question so far. Oakley dokley then. Well, lastly, we had an exponential function, which is all kinds of different. This time, instead of raising the x values to an exponent, we have to use the exponential function to take them as the exponent. The exponential function is exp, so we use exp. It breaks. That is, of course, part of the procedure. You guys just don't mind me. How are things? Good. Expo. That'd be muscle memory. Yeah, Expo. Stop writing the word Expo, John. So, how long do you suppose we should do this before I inevitably give up? Should we just have this be the rest of the hour, just me struggling with Excel?
Maybe we should draw the sheet out.
Okay, so here is the other skill that is important in engineering homework, of course. Linest, exponential. I swear I did that right. Yeah, Float, right, polynomials, great. Control-Shift-Enter, we're way on top of you there. A natural log of x, oh, right, duh. I asked for that. Not being in the caret of the e, that was bizarre. Well, because of that only having a single argument, it makes no sense for us to put it in 4 cells. Let's break that back out into its regular array function. Of course we can't. It would be a shame if everything went according to plan. There we go, much more better. That is how you get the coefficients in the case of the exponential function. Since we want the y values to be as a result of the exponential, we have to take the x values as a natural log. Bringing it over to the other side so we have y by itself. Questions on that process? Well, good news, bad news. The good news, the bad news first, of course. The bad news is that you did not have the Excel videos to be able to access and figure out what we had done in class, which normally wouldn't be that big of a deal, except I've been doing them all semester, and as a result, I think quite a few of you have grown reliant on them and are expecting them to be available. So the good news is that the homework today won't be due until midnight tonight. So if you want to go back and change any aspect of your homework assignment, you are welcome to do so. We will grade the most recent submission to the Dropbox. You get no longer than that. Still live? What would you like your title to be? The Grand Emperor of live streaming? Done. Okay. So today I want to explore the idea of doing analysis with a unknown number of splits in your analyses. So in some situations when you are running through a repeated calculation, you know how many times you need to repeat it ahead of time. In some situations you don't. That's the distinction between the for loop and the while loop in MATLAB, is do you know how many loops you need to make ahead of time? So I want to apply that as an equivalent analysis in Excel. And to do that, we are going to be using something that doesn't make a whole lot of sense to do in Excel, but I think it's something that you guys probably have your head wrapped around already. So forgive the bizarre example in the meantime. Statistically speaking, about a quarter of you have taken calculus, and the remainder of you should have at least taken pre-calc, because it is a prerequisite for the course. So those of you who have what is the result of this thing? How do you know that?
Because you take the integral, so it's going to be, since the 3 is a constant, you pull it out, and then the integral of x squared is 1/3 x cubed. And the 1/3 cancels out with 3, divided by 2, you get 2 cubed, which is 8.
Correct. Another way of doing this would be to split it into a numerical solution. In some situations, you find yourself able to do the analyses ahead of time and do the math yourself. In other situations, you want Excel to do the heavy lifting for you. For example, one of the things we're going to be doing in my fluids class tomorrow, my fluid mechanics class tomorrow, is we're going to be showing how the volumetric flow rate through a pipe changes as a function of the pressure driving the flow through the pipe. Spoiler, it's essentially the same analysis as if you're analyzing an electrical circuit, because voltage driving electric current is the same, it's pressure driving volumetric flow rate. Spoiler alert. So in that case, we are performing an analysis, and we want it to handle a whole bunch of different calculations. We want it to permeate the same analysis through a whole bunch of different values for pressure difference. We don't want to do that math. We'd be there literally all day. It took us an hour, a whole class day, just to do one analysis by hand. So in that case, it makes more sense for us to set it up inside of computer software, like for example Excel, where we are running it through a whole bunch of different x values, outputting different y values. That way we can plot them or do whatever else we want to, like for example creating a line of best fit. So in this case, this 3x squared value is going to create a graph that looks something like this. The integral is determining the area under the curve. If we don't have the power rule in our toolbox to be able to analyze this system, another way of analyzing it would be to split it into a set number of geometry problems. For example, if I split it into 4 chunks, I could set up a value at 1/4 of the way between 0 and 2, which would be 0.5, 1, 1.5, and 2. Then I could use either the left-hand side of this rectangle to create a polygon that we could figure out the area for. We could use the center, which is something like this. We could use the right side, creating a shape like this. And by figuring out the area of those individual shapes and summing them together, we get an approximation for the area under that curve. Theoretically, if we were to take an infinite number of rectangles, we could come up with an exact number for the area under the curve, despite the fact that it's a curve. This is called a Riemann sum. Are you all familiar with the Riemann sum? Cool. So my goal is going to be to set up an Excel workbook that can take any polynomial and figure out the area under the curve by splitting it into a certain number of Riemann sums. So to do that, let's set up a column for x values. Let's set up a column for y values. Let's set up a column for delta x values. And then let's do the left side Riemann sums, right side Riemann sums, and then the trapezoidal method, which is equivalent to the middle of that rectangle. And I want this table to be able to accommodate any number of rectangles that we could throw at it. Realistically, I can't do any number. If we were to add in, say, 1,000,000 rectangles, that's not something that we could set up in Excel and still have it calculate a result on this potato of a computer in front of me. So instead of 1,000,000, let's go with, 1,000. Think 1,000 is reasonable? I mean, we could go to something like 10,000 if we wanted to. So I'm going to scroll down for a while. You guys remember how many columns we had? Was it 5? I think it was 6. Okay, let's just hope it was 6. So I'm going to grab the 1,001st row. I'm going to go back up to the top. I'm going to highlight this area. I'm going to format this as a table. I'm going to tell it that it has headers to accommodate the fact that I specified x, y, delta x, left side Riemann sum, right side Riemann sum, trap. That way I can have this table populate with information that I specify. Grand Emperor, are we still online? Thank you much. Okay. Now, let's break apart the polynomial a little bit here. Let's say my equation is supposed to be equation. Ooh, better yet, let's break this into multiple cells. 4 cells. Let's go with 4. So if I break this into 4 cells and I call this equation, and this is going to be y is equal to a times x cubed plus b times x squared plus c times x plus d. Then I'm going to specify values for a, b, c, and d in these cells below them, and I'm going to make them be yellow so that we can keep track of what are supposed to be user inputs. So let's say that I wanted to actually use 3 times x squared here. In that case, b would be 3 and everything else would be 0. The next thing I'm going to do is establish my lower bound and my upper bound. In this definite integral, we went from 0 to 2, so let's repeat that here. Upper bound. You guys will have to excuse me. I'm typing with a bit of a cold. Upper bound. That's much more better. This time, I will make them 0 and 2 as well to be able to accommodate any arbitrary lower and higher side. Let's add in a step size. Maybe the step size is supposed to be 0.5, like this. Now, to make things a little bit easier, I'm going to name these individual cells so that we can reference them. So I'm going to call this lower bound. You guys think that's a good name? I like it. And then maybe upper bound. And did I spell it right? Ha-ha! Okay, then step size. Cool beans. Now, what do you suppose we should call this value? Well, I feel like A works. Maybe B. Maybe C. Whoops. C. Maybe C. I don't know if it likes that either. The problem with going into individual letters like this as names is that sometimes it won't allow you to specify a name that is reserved for something else. So if I make this equation and I call this C, we're not going to be able to go with that. The reason we can't reference C is because it's a pre-programmed constant. We have to come up with another name. How about C? I like it. That's great. So we have A. Okay, I don't like this because this is different. So let's continue this. Let's go with A. Now we have A and A, both as relevant names. B and B, both as relevant names. And D and D. So we have multiple names assigned to A, B, C, and D. If I want to be real particular here, I can go into my name manager. I could get rid of some of these. Like, for example, if I only wanted to call A, B, and D by their proper names, B, D, A, and C, I can get rid of the other names that we had specified. Now we have A, B, C, and D. I like that. A lower bound, upper bound, step size. Great. So my goal is to write a single function into the column for x, which will output 0 in the first value, because that's the lower bound, In the second value, I want it to output 0.5. In the third row, I want it to output 1. In the fourth row, I want it to output 1.5. In the last row, I want it to output 2. After that, I don't want it to output anything. So how do you suppose we should do this? Well, I will give you a hint. It's going to involve the row function. The row function returns the current row that you're in. So if we put in row with no argument, that will use the current cell that we're in, and it'll output the row number corresponding to that particular cell. In this case, we are in row 2. In this case, we are in row 3, etc. So if I were to take row and subtract 2, now we have the index for the cell that we're currently in. Can you think of how we could use that along with our lower bound, upper bound, and step size variables to create what we actually want? Yes? Well, what would dividing by 2 do? True? True. That's great. However, if I divide by 2, I'm only going to have correct values if my step size is 0.5. I want to create a sheet that is able to handle something else, maybe 0.75 or maybe 0.005. Well, if we divide by 0.5, we're going to be multiplying by 2. There we go. We take row minus 2 and we multiply by step size. Anyone see a problem with that? There are 2 problems. 1, it keeps going. 2, it only works if the lower bound is 0. If the lower bound is negative 2, for example, it doesn't work. So can you think of a way that we could modify this to accommodate that second error first? How do we start at lower bound instead of starting at 0?
Do we have a function like linspace space in MATLAB or in Excel?
We don't. What we're essentially doing is building one. I like where your head's at, though. You're paying attention to MATLAB. So again, our problem at the moment, the problem on the table, is right now our lower bound is 0, which means this works just fine. But if our lower bound changes to 2, this first cell needs to be negative 2, not 0. We could, but I need this number, which is outputting how much to step each time, to be unaffected. We can. We could put it here, but then we would output the row corresponding to lower bound, which is 5, every time. How could we modify this function, including the value of lower bound, to output negative 2? Right now it's outputting 0. Exactly. We could add lower bound to it. If we add lower bound to it, then when lower bound is negative 2, it starts at negative 2. When lower bound is 5, it starts at 5. Good. Does that make sense? The next thing we have to address is the fact that we are counting past our upper bound. So to handle that, I'm going to throw in a logical statement. I'm going to say, hey, this thing that we just wrote out, I'm going to copy that, and I'm going to say, if that thing is outputting a value that is greater than upper bound, output nothing instead. The way that I output nothing instead is quotation mark, an empty string. So now I'm using an if-then statement, which inside of Excel is just an if function, which takes 3 arguments. The first argument is the thing to test. Second argument is what to output if that test is true. Third argument is what to output if that test is false. So the thing we're testing is, hey, does that thing that we just wrote output something greater than upper bound? If yes, it outputs nothing. If no, it outputs that thing. If I hit enter, I get what I wanted. And if I change this from 0 to negative 2, I increase the number of cells that have values in them because I have to take more total steps now to get from lower bound to upper bound. Does this method make sense? Now, technically speaking, I run into a bit of an error if I were to change step size to a value that did not allow for what we wanted. Like if I change this from 0.5 to 5, I don't step up and reach the upper bound. So we could modify our function to be able to handle that, but within the scope of this class, since this is only an example for getting us practiced at handling a table that only actually uses part of its values, this works just fine. Now, I want to calculate the value of y at that x value. How do I do that?
That equation, like, instead of x, use the cell next to it.
Exactly right. So I, of course, take a, I multiply that by x cubed plus b multiplied by x squared plus c multiplied by x to the first power plus d. Now, of course, instead of typing multiply after b, I put an ampersand. There we go. Any other glaring errors in that calculation?
Is the raised to the first power necessary?
It isn't. We could get rid of that if we wanted to. Well, if I hit enter, let's see what happens. So we output a correct value in row 1. We output a correct value in row 2, row 3, row 4, row 5. All great. Row 6, though, it breaks. It breaks because it's trying to take a, which is 0, multiplied by nothing. Not 0, nothing. Which is a little bit problematic. How could we modify this function to be able to handle those empty rows? We do the same exact if statement we did earlier. In fact, if we wanted to, we could modify this and instead write if that value in the cell to our left, x, is not nothing, output the actual value that we want. If it is nothing, output nothing. So the way we test for nothing is less than, greater than, quotation mark, quotation mark. So that's saying if x is anything other than nothing, output this value here. If not, output nothing. Another way of doing that would be to use the isBlank function. IsBlank would output true if that cell were blank, false if it isn't. Okay, so far so good. Now delta x needs to output the value between this current x and the previous x. So what I want is nothing in the first cell, and then in the second cell, I want it to return a value of 0.5. I know that because we're taking 0.5 minus 0. And then in the row 3, I want it to output 0.5, because that's going to be the value between 1 and 0.5. How could I write a function that outputs the value of our current x minus the previous x, except for the first row where it returns blank? Any ideas?
You just subtract them, putting like an absolute value on something.
We can. We could just subtract them. Like if I were to type into this function here, this current x minus the previous x value, the problem is, with this as written, we fail for the first row, and we fail for every other row. More logic. Good. What would you like to say is the first logical piece?
If it's in there, if like x is filled in, if it's not nothing.
Correct. If x is not nothing, do the thing, otherwise output nothing. That's a good start, except it's still failing on row 1. How could we modify that? If x is 0 would work for this particular case, but remember, we want it to be able to accommodate any lower bound, including like -2. And it still fails on row 2, or excuse me, on the first row, even though that value isn't 0.
So you usually say if the x is equal to the lower bound, then it should be nothing.
Totally true. We could say if x is something that isn't blank and x is equal to lower bound, output nothing. That's totally fine. The way that we include multiple logical statements is to wrap them in an AND function. The AND function can take as many arguments as you want, and it outputs true if the result of the logical test inside of each of those arguments are themselves true. So I want AND x is not equal to 0, comma, x is lower bound, which I had cleverly named lower bound for just such an occasion. So inside of the logical statement of if, I have an AND function. And inside of that AND function, I have two tests. This now is returning true if x is not blank and if x is equal to lower bound. What's wrong with this current logic? Correct. I need to switch the logic on this second statement. So I could say is not equal to, but Excel doesn't handle not equal to as a logical test. So what I have to do is instead put that inside of a not function. The not function just reverses the logic inside of that statement. There we go. Now we have a test that works. Does this make sense? Another way of approaching this would be if instead of using not is lower bound, we could also say if rho is greater than 2. That would also work. You do what you like. Okay. Now what I want to do here is output for each value of delta x. I want to output what the height of that rectangle is. I want to use the left side Riemann sum. I want to use the right side Riemann sum. And I want to use the middle. So for each one of these delta x values, since each one of those represents a rectangle, I want to output a height of that rectangle. How do you suppose we do that? Well, again, this rectangle, which has a width of 0.5, is between the x value of 2, negative 2, and negative 1.5. If I wanted to switch this back to 0, that might make it easier for us to keep track of. 0 over there is the height of the first rectangle if we're using a left-hand Riemann sum. That first rectangle is represented by this first 0.5. So I want this value to output 0 for this first rectangle. If my lower bound were something that was like negative 2, for example, I need this to output 12. How could I write a function that outputted 12 for this cell? It's totally true. We could. We could just say, is that so? Right? Problem with this is right now this is going to break anywhere that isn't actually within the numerical part of our table. So up here, it's grabbing the value y. Furthermore, we only want this to output cells in a place where there is a rectangle. So we don't want a value here, and we don't want a value here. So I need to add some logic. What logic do I need to add to this? Guys, collectively, you have the power. You've got the magic in you. Every time you something turns into gold. Now everybody knows you've got the magic in you. What do we write in our logical statement? If? Okay, great. I like it. If. Good start.
You say if, then the and statement, or be both, below row 2, or like, I don't know how to word it, but so it's like.
If below row 2 and.
And then if it's,
Like that? Well, let's see how this works. It's failing every time. Remember, we right now are evaluating if the row number is less than 2 and if x is greater than upper bound. Is and what we want? Let's try or. Okay, we are making progress. Right now we're outputting true everywhere that isn't what we want it to be. And also we have this 0 in our first row. How do we modify this? Do it. I mean, that would work, but then we'd have to invert the logic. Can you think of another way of evaluating if it isn't greater than? I mean, less than isn't quite what we want. Less than or equal to, right? So we want less than or equal to 2. That outputs 1, or true, everywhere that isn't where we want the thing to happen. So if instead of 1 here, if I change this to nothing, now we have zeros. And instead of 0, I put the previous y value. Boom. Now we have the height corresponding to a left-hand Riemann sum rectangle at that delta x. I know. It's a big moment. We did it, guys. Mission accomplished. Except, oh wait, we have a right-hand Riemann sum as well. What's the difference between the left-hand Riemann sum for this first rectangle and the right-hand Riemann sum for this first rectangle? Correct. So what I want to do here is do the exact same test, except instead of outputting B2, I want to output Y. Does that make sense? You guys on the same page so far? Okay. Cool. Questions so far? Emperor all good? Sweet. Now, what's halfway between 12 and 6.75? I mean, average works. We could try that. We could go halfway between them by using the average function. The average function would take 2 arguments here. One would be the left-hand Riemann sum, one would be the right-hand Riemann sum. Oh, wait, that fails everywhere that is blank. How could I modify this? Let's use some logic. What specifically? If what is less than? If it's not nothing, if what's not nothing?
The one to the left.
Sure. If the one to the left is not nothing, then output what?
Something.
Something? Something. And if it's not?
The function.
The function. Then? Okay, so we're outputting something everywhere that we want there to be something, and we're outputting the function then everywhere that we don't want there to be something. So if I switch the function then to be, in fact, blank, now we have something only where we want something. And instead of something, we put in? Correct. There we go. Now I have a height corresponding to this first rectangle using the left-hand Riemann sum, right-hand Riemann sum, and the trapezoidal method. More importantly, we have a skill set that allows us to handle creating as many rows inside of a table as we actually need. Theoretically, we could change this step size to be like 0.05 or 0.01, and it'll figure out however many rectangles it needs to and only include calculations for that many. Does that make sense? So then in order to actually come up with the area, we could do left-hand Riemann? That looks right. Left-hand Riemann sum. Let's not attempt to spell that again. The right-hand Riemann sum and the trapezoidal sum. Then I will, let's just merge these cells together and output an area here. So this would be the sum of everything in the left-hand Riemann sum. That table multiplied by this table here, delta x. If we wanted to do it this way, we don't want the sum of each individual value. We want the sum of the multiplication of each individual value. So How do we go about figuring that out? Like I want to add together the areas here. I want 12 times 0.5 plus 6.75 times 0.5 plus 3 times 0.5 plus 0.75 times 0.5, etc. Control Shift Enter, like this. I mean, what you're saying is use an array function. That's true. We could do that. The problem is, right now we are trying to evaluate the sum of nothing times nothing. Again, we run into a little bit of an issue right now because the way that we set up our function, we have nothing times nothing, which is returning an error, not 0. We could use more logic. We could say if the value is below and add that into our calculation over here. We could figure out the area instead of the y value. For example, if we wanted each of these to be 12 multiplied by 0.5, I could take just this result and multiply it by delta x. That's also totally fine. If we add that in here, this would be b2 times delta x. This would be y times delta x. And nothing times delta x, or average times delta x. That's totally fine too. Doesn't really matter. If we do it this way, then we just sum together this left-hand Riemann sum column. If we did it the other way, we would just have to change our nothings to 0. It doesn't actually matter. But in general, we now have a function inside of each of those 3 columns which outputs the area of the rectangle instead of the height of the rectangle. We could simplify this even further by getting rid of delta x and putting this function inside of this part of the calculation in place of delta x. We could actually simplify it further by putting x and y inside of this single function and only do a single function in 3 columns. But for the moment, I think this is just fine. This is a little bit more piecewise, and it's probably easier to wrap your head around. So the cool thing about this is if we change this from -2 to 0, we should end up with 8. We have 5.25, 11.25, and 4. Not great, but we could increase our step size, or excuse me, we could decrease our step size, increasing the number of steps. If we change it from 0.5 to 0.05, we now get values that are closer to 8. And 0.005, we get values that are closer to 8, except for our trapezoidal sum. What do you suppose is wrong with our trapezoidal sum? Like here, maybe it'll be easier to see if we jump back to 0.5.
Still taking the average, and now it's taking the average of the areas, not the heights.
Correct. We need this to not be multiplied by delta x. Much more better. So with 0.5, 0.05, we are converging on 8. If the exact answer is, let's make this a yellow cell as well. If the exact answer is known in this case, we could figure out what those values are. Say area, and this is percent error. By taking, again, the absolute value of this value minus this value, I'll use an absolute reference so that I don't have to retype in this function, divided by the exact answer, expressed as a percentage, add in a couple more decimal places, populate that down. Now if we have 0.05, we have 4% error on the left hand and right hand, but 0.04 on the trapezoidal sum. 0.025, 0.0005. That breaks it because we don't have enough rows in this table. We only selected 1,000. So we have to make sure we don't have more than 1,000 steps. By the way, if you want to, if you have a relatively powerful computer, you can actually just take these 5 rows and generate a table. And it'll make a table using all of the cells in that row. Excuse me, column. Not 1,000 rows, not 10,000 rows, but all the rows. Which, depending on if you have the 32-bit or 64-bit version of Excel, is a whole bunch. Right now, on this potato, I'm guessing, oh, hey, that's not too bad. Let's see what happens if we start populating in some functions. Shall we? So, how many seconds before the stream fails?
Do you have a fire extinguisher?
I think there's one back there somewhere. Okay, so this worked okay, and it is referencing 1 million and some cells, but it's also beginning to fail way down here. We probably shouldn't do that on a computer that is so taxed by just streaming something to YouTube. Anyway, if you want to have fun stressing out your computer, you're welcome to do that. Your homework assignment this week is to play with this idea a little bit. What I want you to do is create an Excel spreadsheet which approximately accurately outputs the values of the integrals of all of these functions between certain ranges. So you should have a single Excel spreadsheet for problem 1, a single Excel spreadsheet for problem 2. Problems 1 and 2 are very similar to the example we just worked in class. I'm guessing you're going to want to reference the video. Is it still up? Second on your job, you're packing up. Man, it's only 4:19. Your shift is not over until 4:20, Graham Demper. It's fine. Sorry for continuing to reference you. It's just that you're one of 2 people that have titles now, so I can do that. The third problem, however, is a little bit different. I'm asking you to do some fluid mechanics analysis, which doesn't actually require that you understand fluid mechanics. For the purposes of this example, you don't have to think about things. All you have to do is figure out the integral of this equation, where v is this separate function here. So lowercase r is the thing that you're using, the step, the x equivalent. Uppercase r is 0.25. It is a constant. 1 is a constant. V max is a constant. And n is a constant. So it looks scary. It's not as bad as it looks. Make sense? See you guys next week. Remember, you don't have class on Thursday. This class on Thursday. You probably have other classes.